Okay, so after way too long a delay, so today's lecture is pretty much follows Cover and Thomas. So the suggested readings here are pretty close to what I'm going to cover. So you guys are being recorded, by the way. We are being recorded for posterity. Okay, so the lecture is going to follow Cover and Thomas pretty quickly, and then the two lectures this week are, we're going to take the notion of entropy as a measure of uncertainty and generalize it to deal with sort of arbitrary, finite valued, discrete stochastic processes. And shifting from this notion of information as uncertainty to ask what we can understand about the structure of processes as revealed in the sequences they produce and the information in those sequences. That'll be pretty much the theme of the rest of the course, but today we're going to shift most of what we're going to cover today, and almost all of Cover and Thomas is about processes that have no memory. They're independent, identically distributed, which are exactly the class of processes we do not find interesting or will not find interesting, but it's a starting point. And so the burden of the class is to first introduce us to the basic ideas of information theory in Cover and Thomas, and then show how they can be extended. There is, to help with the homework and also just to kind of follow along with some of the examples today and Thursday, a new interactive lab I put up under Sage that lets you define your own processes and compute word distributions. Those mosaics I was showing you before for word distributions, because we're going to start studying those word distributions in some detail, asking how much information and what kinds of information the word distributions exhibit. Also, the lab shows you how to define your own machines. So there might actually be some homework problems that say, oh, write down a Markov chain or hidden Markov chain. And so I think at the bottom of the worksheet, there is helper code and instructions for how to basically type in character strings that specify states and their names and edge labels, and then it gives you a function back that will print it very nicely and lay it out for you. So work through this. Homework requires some of the code that's in there. Okay, so last time, the first dipping our toe into information theory was just to use Shannon's notion of surprise, what he claimed was the self-information of events, and we averaged that to get that p log p form of the Shannon information in the distribution P. And we're going to stick with that a little bit today, and I also feel a little bit obligated to tell you some of the technological importance of information theory, even though we won't use it directly in the next couple weeks. So we'll talk about compression and compressed data, which will give us a reinterpretation of the entropy rate, the Shannon entropy of a random variable or an information source. And then the question that really motivated Shannon originally was, how do we communicate that information over some channel, over wires, over wireless, over... and so the Golday are really the two main theorems of information theory, so-called Shannon's first theorem, that you can't compress any better than the entropy of a source, and that kind of a constructive way, you can actually transmit information in a source error-free up to rates governed by a channel's, communication channel's capacity. So we'll have to define what that is. And it's quite amazing. Those two theorems underlie so much of communication theory and even the design of the internet and all these communication channels we now use, whether it's wireless microphones that don't work or Bluetooth connections or Wi-Fi. Underneath all of this really is this very constructive approach that Shannon laid out in the mid-40s, that there are ways to encode information and reliably transmit it, even error-free, over channels that have distortion, noise, and so on. So, okay. The net result of this is going to be deepening our understanding of what the Shannon entropy is. That gives a perfectly operational and engineering meaning to this. Now, I am just covering these really deep ideas in essentially one lecture because we have to move on. We have other fish to fry. But I would suggest, if you haven't done it already, going back and reading through the Cover and Thomas chapter on the Shannon's second theorem. Again, it's such an important idea in probably the history of 20th century science and engineering. It's worth knowing a little more. This lecture will just give us, kind of like other topics, a little bit of an overview and try to motivate the ideas and tell you what the strategies are. I'll talk about why this is true. Cover and Thomas actually prove it. So, okay, so here's the domain of discourse, and this is laid out actually in Shannon's original paper in the mid-40s, his notion of a communication channel, right? He was a researcher at Bell Labs, and Bell Telephone Laboratories was interested in efficient ways of designing communication networks and maximizing their utility and performance. So he came up with this notion of a communication channel. It's a model, and the idea is that we have some source of information. You know, could be the videos of the lectures, could be the Encyclopedia Britannica. There's some source of information, and we want to get it from basically point A to point B, from you to someone that you want to have look at that information. So we have an information source. That'll be some random variable over some alphabet. And it produces, in the language, a time series of messages. You could think of this as a series of letters in written English, or words as tokens. You can think of different kinds of tokens, but anyway, you have a time series of messages. And then somehow those messages get transformed. So I was trying to have the messages in my head during the lecture transformed into pressure waves that then was going to be transduced by the wireless mic into a radio frequency signal that then the receiver was going to reconstruct error-free, hopefully. So there's some sort of encoding here where the messages get translated. You can think of this as adapting to the system we have. Back in Shannon's time, we just had basically batteries and wires, not really any decent amplifiers. So there's some sort of encoding. We'll think of this all kind of abstractly today. And we end up in transforming the messages into a series of code words. Now these code words are presumably designed to adapt to the communication medium, the channel, and done well can compensate any corruption that comes in. So we're going to think of the channel here as basically just a one-step conditional distribution described by a certain code word coming in. I'm going to get some possibly corrupt code word coming out. And then, at the far end, the receiver has to somehow decode these corrupted code words, returning the original message. So in this, the goal is, whatever the data is here, whatever the raw information is here, we want it to appear over here with no errors. And the amazing thing is that Shannon showed that there are ways of measuring the amount of information, tells us how much we can compress, and that there exist ways of building code books, or codes, that can compensate for errors in the channel as long as certain basic quantitative thresholds are maintained. That's the second theorem. Basically, the information rate, the rate at which the source is producing information, that has to be sort of less than the rate at which the channel can transmit the information. As long as that's true, he shows in a non-constructive proof that there will exist codes that will give you error-free transmission. It's kind of amazing. So that's the overall setting and the goals. Now, some of the basic definitions and notation. So we have our information source, some random variable that's distributed, some distribution P. Again, this is where the IID assumption comes in. Each message is drawn from this distribution independently. It's the same distribution for all time, IID. Okay, we have some set of messages. I'll just assume we have discrete messages, although information theory in continuous domains is quite important. Now, we're going to have a code. We want to translate this message into some sort of code. Typically, just for simplicity, we'll take a binary alphabet. But your choice as a communication engineer would be to adapt this to whatever channel you have. We'll just assume the channel deals with binary alphabets. typically. And then the code words are just basically the union of all single letter, 2-letter, 3-letter code words. Okay. Just another D plus here. Whole set. And we have to choose between those. We want basically a mapping from message realization to code. And then L of X will be, that'll just denote the length of the code word that we've chosen to associate with X. Okay, so the result of engineering process, in fact, Shannon's non-constructive proof indicated that there were solutions, and since the mid-40s, there was a small or maybe even large industry of people trying to find good ways of building code books. It's basically, well, it's well understood now, but originally, and even for some coding questions today, there's a bit of an art to discovering ways of building these code books. So the result is some mapping from messages to code words. Okay, that's the code book. It's just a lookup table, just a big table between messages, A, B, C, D, or words, or alpha, beta, gamma, into some set of binary words, if you want to think about the simple case. And we can measure the performance, or at least the size of the code book, by just looking at, we weight the lengths of the code words associated with each message with its probability of occurring from the source. That gives us an average measure of, something that the channel will have to handle. So this average or expected length of a code word. And sometimes it's called the code rate. It'll be average over the message's probabilities, the length, or we can just think of this, I've got a code book, I put it in, there's this kind of metric for performance of that particular code book, which we'll compare to see how well we can do. So the result of all of that is that we end up with an encoding. So we have this message source producing a time series of messages, and then we end up with this concatenated set, a time series of code words. Maybe going from 26 letters down to binary strings. Okay, so notice that if we had a certain size of message alphabet, say 26 letters, then if this average code rate was less than that, we'd actually achieve some level of compression. And we can just send the raw messages and give them unique fixed length blocks, binary words, but then we wouldn't have compressed anything. But there'll be ways of choosing how we associate the binary words. Basically, the idea is to associate short code words with highly probable, often used messages. And we then get this code rate down below the average size of the alphabet, it's the message alphabet itself. So here's an example to make all these things concrete. This should look a little bit familiar. So our input alphabet has 4 letters, A, B, C, D. We're going to go to a channel that only accepts binary symbols, so we have to do some translation. You could just naively say, oh, I've got 4 things here. I'm going to associate all the length 2 words, 0, 0, 0, 1, 1, 0, 1, 1 with that. And then you wouldn't get any net compression. So we have this distribution. Again, this should look familiar. A, probably a half. B, probably a quarter. C and D, probably 1/8. And last lecture, we calculated the entropy rate for that information source. That was 1 3/4 bits. Okay? So the interpretation last time was the 1 3/4 bits. That was the average number of questions you would ask over many trials to figure out which of the 4 events occurred. So now what we're going to do is just essentially pick out of the air, this one happens to be optimal for this case, a code book, which is just an association between the messages and code words. So notice, I've done what I just said. I've associated, out of all the binary strings I could associate, I could be stupid and have like a million binary strings. But what I've done here is associate shortest code word with the most probable message coming in. So whenever I see A, this encoding device is going to output string 0. When it sees B, it outputs 1, 0, and so on. And I can go through and calculate that code rate, right? That's the length weighted by the probability of the messages coming in. That's certainly less than log of 4, right? And the code rate is 1 3/4 bits. So there's a possibility of some compression here. By choosing code words that were short and associating with the most probable messages coming in, I've actually been able to compress the code, the incoming messages. Okay. So notice the similarity here. We'll explain why in just a second. So the entropy of the message source was 1 3/4 bits, and this particular choice of code words, the output process has a code rate of 1 3/4 bits. Okay, now there's a problem here when we just start, when we're choosing a code book like this, right? We have a time series, in this case of AB, A, B, C, D, D coming in, and now we're laying down binary words, but now we have this long binary string that doesn't necessarily tell us where the beginning and ending of the code word blocks are, right? So we have to, there's some constraints. There are particularly judicious ways of choosing the binary words so that we can actually find out what the framing is. So that's this notion of different kinds of code. So the first thing we want, first kind of constraint when we're designing a code book, is that we want a non-singular code. That just means that when the messages are different, the code words are different. We don't want ambiguity at that level. That'd be kind of silly. If I should say the A and B 0, the code word 0, then the receiver getting a 0 wouldn't know which I meant or which occurred, A or B. And we can now talk about the extension of a code book, which is just some way of talking about all the concatenations of the code words. So we end up with a source words of length L like this. And then we have the corresponding code word for that, which just applies the code book to each symbol separately. And what we would like is that when things get concatenated this way, that it also is non-singular, that we don't have this ambiguity. In other words, if I have a long string of the encoded sequence, this long binary string, I can recover the original sequence of messages. And one way to do that, so that's called when the code book concatenated with itself is non-singular. It's particularly parsable. It's called uniquely decodable in that case. And here's one example of that, called a prefix code. The idea here, which will give us uniquely decodable, is that no code word is a prefix of another code word. You can kind of imagine as I'm scanning along, I'll always kind of be framing things just right. So you don't have to look ahead to see that there's some period at the end of a sentence or some complicated German sentence where the verb occurs at the end, something like that. You don't have to scan ahead. You're always kind of tracking along and finding the boundaries that are associated with code words and then therefore their messages. So let's show, go back to the example. We had this code book for that example, and so if we had A, C, D, B, A, C, I would code that in. A is a 0, C is 1, 1, 0, D is 1, 1, 1, B is 1, 0, A is 0, C is 1, 1, 0. Okay. So just lay it out. So that's all the encoder. Once you design the code book, the encoder as a device is kind of simple. But now we're worrying about downstream. If I just gave you this, well, and the code book, how would you parse it back? So notice now that if I come in here and I go, oh, 0, well, there's only one word that starts with 0. So I uniquely see that framing. Okay, fine. I output that. Then I come up here and I go 1. Well, there are 3 words that are 1. 1, 1. Well, there are 2 words that satisfy that. 0. Oh, it's actually C. 1, 1, 1. Same thing again. There's 3 words that begin with 1. 2 words that begin with 2 1s, and there's only 1 word that has 3 1s, and so on. So you can actually go through this because it's uniquely decodable. In other words, it preserves the non-prefix condition preserves the framing for the decoder. So that seems like a simple criteria when you build a code book. Another word should be prefixes of others. There's a simple algebraic characterization of a code book. It's called the Kraft inequality. Sum up 2 to the minus length of each code word, and if that's less than or equal to 1, then you have a prefix code. In a sense, what this is telling us, there's actually a graphical way to think about a prefix code that essentially implements this Kraft inequality. You can think of it as a tree of codes. And the tree helps us keep track of not accidentally choosing a code word that's a prefix of another. So that previous code book is the words, I'll just point out we had 0, and that was the code for A. 1, 0 was the code for B. 1, 1, 0 was the code for C, and 1, 1, 1 was the code for D. That craft inequality, in a sense, is imagine I have sort of unit mass up here, and I keep dividing that in pieces. The inequality assumes you're sort of splitting that 50-50. And so the tree represents that algebraic craft inequality specification for it. So that's obviously something you can calculate without laying out the tree. So here's the sum. Right? Just go 2 to the length of A, 2 to the minus length of B, and so on. And in this case, for that code book and that initial source distribution, it is exactly 1. In a sense, I'm kind of splitting up. Remember our game of 20 questions. Right, splits us 50-50, and then for the 3 codes that are left over, I split 50-50 again, and split 50 again for the last 2 words. So it exactly sums up to. Okay, so that's a graphical representation of being a prefix code and the craft inequality. So, but the goal here is to define these codes. You know, typically the information sources coming in aren't going to be 4 letters. They're not going to have that nice power of 1/2 distribution over event probabilities. So, very complicated statistics. You can imagine trying to do this for all the words in a dictionary or all of written English or something like that. There's obviously no simple distribution for that. So, hence this industry of trying to design different kinds of code books that are well adapted. I mean, there are rules in English, right? U usually follows a Q. That's something that's predictable. Therefore, since that is, a rule, I can use that to constrain my anticipation of letters that follow Q. I can build more efficient codes because of that. Okay, so we need some sort of general constraints on designing these code books. And so what I've said before basically sets us up for these 2 criteria. Okay. What we're trying to do is we want to find a code book that minimizes the expected code length, because that's going to minimize the amount of information we're pushing down through the channel. Or the other way to think about it, it's helping us compress the redundancies in the information source. And then we want it to be decodable, so we use this criteria here. It's algebraic criteria, the craft inequality, so that it would be uniquely decodable. There might be many, many solutions to this, but they might be, you might have to look at the whole message before you went back and figured out where the boundaries were. This says sort of local decodability. I can kind of decode on the fly. So we use the craft inequality. Well, now we have these 2. These are components of a cost function, and we can try to optimize them using Lagrange multipliers. So we've got this cost for a particular code book, the average length, and then how well it satisfies or doesn't, this craft inequality. So here's our Lagrange multiplier, and now we just turn the crank, right? We were looking for how these 2 components of the cost function cross over each other. So we take the derivative of the cost function with respect to L and end up doing the algebra here. The net result is that we have the suggestion that there's this relationship between the 2 to the minus length of code words and the probability with a normalization constant. In other words, this lambda is the Lagrange multiplier, but the claim here is that we found the optimum when the length of the code word is minus log of the probability of the message. That should look familiar. Channel self-information. And then just one step down here, if I look at the average length, you see that in fact that's just p log p, so that's the entropy rate, the entropy of the message source, of the information source. So this gives us another way of thinking about what the entropy rate is. When we, given a distribution, we calculate this. We may not have a code book for it, but it's telling us what the optimal code rate would be if we can find it. So at least that's a nice quantitative goal, and every time we come up with a candidate, we can at least measure how far we are from this optimum. And in general, this specification here is not implementable.
Hey, Jay, can I ask a
Yeah,
question?
absolutely.
So I'm a little confused about what the intuition is for why the craft inequality constrains you to have a non-prefix code. Because it seems like you can have, I can sort of see that there's something more complicated going on, but it seems like you can have a long code but still have prefix code and then satisfy the craft inequality.
Right, and that just means you'll end up with all those inverse powers of 2 having small contributions, which will make the sum much less than 1. So that's okay. It allows that. It's just, contrast the example working through is not optimal. So the craft inequality, the way to think about it, right, we're just kind of summing up the lengths in terms of powers of a half. And it really is, you just think about it like think about that upper bound, 1, as the total amount of code mass, if you will, and we're trying to distribute it among code words. So one way to do that and make sure we don't have prefixes is to think of the mass up here, we're splitting it somehow. Just think of it like 50-50, because that's the weight in the sum. We have powers of a half. And then we're just splitting it up as we go down for all of the code words. So it's that sum is a literal algebraic expression of this tree structure. Okay, so this specification, so we just solved, yeah, sure, great.
On the slide right before, why is the constraint? How do you constrain on
Oh, we can solve for once we take the derivative and set this objective function's derivative to 0, then we can solve for the relationship between lengths and probabilities, and then we just have this at that optimum. You can solve for lambda. Go back up and you can solve for this. Just plug that solution back in. You get an equation of lambda that is this. Okay.
So is there an implicit summation in that equation?
So here.
Not yeah.
Here. Well, it has to be satisfied for each code word.
So this,
I mean, yeah, each code word in each message. Yeah, it's a concern on them. Sure. Okay. So the next point here is that that prescription that we should try to choose a set of these code word lengths that are given by minus log of probability. Well, code words are integer length. Therefore, we can't do this, which will be some fraction, typically some fraction. So there are ways of getting around this. So this is the first kind of example of how, although the theory tells us there's some optimum, there are design issues when we implement things. So what you can do, of course, is just pick code lengths that are, the integer larger than this real value minus log of probability for each message. The Kohler-Thomas book goes through, it's called the Huffman code, which is a prescription that gives you a length that's bounded between the information source entropy and the entropy plus 1, which that sounds pretty good. However, this can be a large cost because this is an additional bit per message coming in. And if you had a very long message, initial data was very long, that could add up to a considerable extra cost. So again, there is a whole subdiscipline of coding theory that tries to develop codes that are appropriate for different kinds of data sources and also that adapt to the kinds of channels you have. Completely separate. Even Cover and Thomas don't go into a lot of detail about designing codes. Now there is a way of sort of tracking. Basically we're stuck in this situation. We have some source that's distributed according to some event probabilities. Our code book, when we're designing things, effectively may use a different distribution. So the question is, how bad can it get? So in other words, we're trying to model this information source, which is given by a probability distribution P, but we in effect have another distribution. So instead of using the distribution of A as a half, B as a quarter, and C and D are eighth, I could have used a different distribution, half a half, a half a half, or something like that. So you can sort of measure how bad your model or encoding distribution is by using the relative entropy. So you can show, Thomas go through this, that the average code length is the entropy rate plus the distance in this informal sense of the information gain between P and Q. And that sets us up for Shannon's first theorem. Basically, that the code rate for any code of an information source is bounded below by the entropy rate of the information source. Can't do any better than that. So it's a goal. Typically, you do worse. The question is how much worse I'm going to do. This gives a more explicit expression of how different they can be. Of course, you can just be silly and choose really bad codings. So you just cannot compress a source below its entropy rate. So that's the other, again, operational interpretation of the Shannon entropy of the source. It's this fundamental limit of compressibility. One way of measuring that is called the redundancy of the information source. Kind of compare this quantity that gives us a measure of the optimal compression we can do against what you might call the identity codebook. So in the case of the 4-letter information source, we just give them 2-bit code words each, and then we have log of 4. So the difference between basically the size of the message alphabet, again, we take the logs here, so they're kind of comparable units, number of bits of the identity codebook versus this optimal indicated by Shannon's first theorem, gives us a measure of the redundancy in the original message source. Again, like I said before, there are, E is the most common letter. There are things we know about this which we wouldn't want to consider Z and use the same size code word as we would with E. So to the extent this quantity is large, so it's log base 2 of 26, which I forget what that is. It's about 4 bits, something like that. People have done empirical estimates of this for written English. It's a little under a bit per letter. So that's about 3 or 4 bits of redundancy built into written English. You might say, well, why is it there? Well, it's part of, a little redundancy does help. If it was completely compressed, and we'll get to an example, we'd have to spend a lot of effort paying attention to what people were saying. Right? Be a lot of detail in there, and redundancy helps kind of spread out the information over a longer time, so you have some chance of recognizing it. In the example case, there's not a whole lot of redundancy. It's about a quarter of a bit. Right? We look at the messages as if it had a Q distribution. It'd be, they're all equally likely. But in fact, the real distribution P has that 1/2, 1/4, 1/8, 1/8 distribution. That gave us 1 3/4 bits. Therefore, a uniform view of the information source would be redundant by a quarter of a bit. So the messages can be redundant. The goal, of course, is that the encoding is not. So there's kind of an optimality we're going for here. We're trying to extract out all of the redundancy. In fact, the short way to say what the goal is here is we want the encoded sequence to look as informative as possible or as random as possible. Okay. So I'm trying to reach, we want the code rate to be the entropy rate. I'll come back to an example where we can look at that more directly. Okay, so that's kind of the first piece of information theory. In fact, I like to think of information theory as really being composed of 2 different large pieces. One is sort of measures of information, and the other is how do I communicate it. So here we get back up to this communication channel. We've been talking about now using entropy of a source as a way of talking about how compressible it is, not so much this uncertainty and predictive interpretation we had last lecture. So there's a question. Okay, I'm able to characterize an information source in terms of its entropy rate. That at least gives us some kind of goal for how we're building a code book for it. But can we do reliable transmission when the channel has some noise built in? How would you do that? So how do you is a way of designing code words maybe that anticipate the kind of noise that happens? And there are lots of examples of that, depending upon the domain. Although they're quickly fading from the technology forefront, hard disks have problems storing long strings of zeros and ones on the disk platter. The electronics starts to drift, and so in fact you have to build a code that typically, it's called run length limited encoding, that if I happen to have 0, 0, 0, I'm putting down on the disk platter, I stick in a 1 every once in a while. That's so that the reading electronics can stay synchronized with it. Otherwise, it'll just drift off, and then the thresholds that are detecting 0, 1 would be so shifted, then you'd start to build up errors. So that's an example of a code sort of anticipating, in that case, a physical property of magnetic storage, and also the electronics, the textual electronics. But microwaves, radio waves, they're all transmissions, all have their own characteristics. That there's a physical side to designing channels. Channels are all over the place, though, not just those. I mean, phone lines, when we do FTP or HTTP transfers, I don't know, human language monologue, like my lectures. More in the spirit of our course, we're thinking about a dynamical system as a communication channel. Right? The idea that however the system is behaving, if you stop at some moment in time, there's some of the history of the system, maybe not all, but some of the history of the system is stored and responsible for the system being in its current instantaneous state. And then somehow that stored information is then used or, say, communicated to the future to produce future behavior. So we can think about the sort of history and future of a dynamical system as being some type of communication channel. Information from the past is communicated through the present moment into future behavior. So this is something we'll come back to a lot and analyze this. You have spatial systems. You can talk about how one or another sites are correlated in a system or half of spin configurations. We've talked about the measuring instrument. We're going from these unknown continuous states into this measurement alphabet through a number of probes and discretization. That's also a channel. And also the learning channel overall. Unknown nature, somehow we have data and we want to reconstruct a model, and the idea there is that we want to recover sort of the hidden message faithfully as much as we can, and also hopefully in the process capture some of the basic observables, properties, and symmetries in the system. So the idea of a channel can be used in many, many different ways, not just in terms of the simple raw communication. So this channel coding problem is basically to overcome errors in the channel. So how are we going to do this? What's the basic strategy? So I'll just give a kind of overview and motivation. The details are in Cover and Thomas, and we'll probably read it in just a few hours. To actually cover it in lecture would take a couple days. We don't have time for that. Maybe we'll come back to some of this in the spring as needed. So there are two problems. So just imagine a channel, it's input-output device. So there are two kinds of errors, roughly speaking. One is called equivocation, where the same input up here leads to two outputs. And ambiguity, where two different inputs to the channel lead to the same noisy code word coming out. Okay. So we have to overcome those things. The idea is to design the code book, do an encoding that lets us compensate for these so that downstream the decoder and the receiver can reconstruct the original message. So the strategy is the following thing. So we want to find the channel inputs, a set of inputs to the channel, code words, that are least ambiguous. Given whatever sort of physical distortion properties we have, like the examples I just mentioned. And then the code book is simply to make a mapping, maybe probability weighted according to message probabilities, onto these least ambiguous code words, inputs of the channel. Okay, so now a little more mathematically, we're going to think about a discrete channel, input X, output Y. We have their marginal distributions, and they're connected by the channel itself, which we represent as a conditional distribution. If I put in a code word, what noisy code word comes out? So it'll just be a simple one-step conditional distribution. It's memoryless. This is the case that's the main focus of Cover and Thomas. In other words, the output at some time t only depends on the immediate input to the channel, no further back. Okay. So then channel says this characteristic of the channel, its transmission rate, if you will. It's called the channel capacity. And it's the mutual information, the shared information between outputs and inputs. Okay. And then we maximize that overall possible input distribution, so it's a characteristic of the channel itself. I mean, sometimes we'll be interested in the sort of the rate at which a channel uses information, I mean, given a particular input. So we don't maximize that, but we would measure that effective rate for a given information source using a mutual information like this. Okay. So the claim is that this channel capacity C is the highest rate that one can transmit information over channel. Well, actually, there's a little more of a twist in Shannon's second theorem, which is reliably and error-free. Okay, well, let's think about what this channel capacity is. Okay, so here we're mutual information between input and output over all possible input sources. And it's helpful to think about at least two extremes of communication. The first is, I got nothing to send. Right? The input is just a completely biased coin, all heads, whatever. So the source entropy is just 0. Okay. Well, what's this mutual information? This channel utilization in this particular source case. Well, we get to choose which expression. So I chose the entropy of the input minus the uncertainty in the input given the output. Well, there's just no information. So the source entropy is 0, and also there's no uncertainty in the output. It's always the same thing. So it's 0. So this mutual information is 0 when the input source is 0. If I'm just using this mutual information as a measure of what's going through a channel. Or you could say a little more, as the entropy, for small entropy rates, the amount of shared information is going to be small going through a channel. Or the other possibility is the channel is just completely distorted. That basically the output is independent of the input. It's throwing all the information away. And then we know that for inputs and outputs, for random variables that are independent, statistically independent, mutual information is 0. So you should have kind of a picture in mind, because we're going to come back to this in lots of examples, actually, that we have a sort of a range of test cases going from completely predictable input to where the input and output are independent of each other. Channels completely distorting. And at both of those extremes, there's no shared information. There's no information transmission rate. But in between is are the interesting cases. And so we're going to have some classes of process that we analyze, where these two cases are going to be the base cases, the easy, trivial cases. Things are just independent, or things are just completely predictable. And all the interesting, this will be our kind of criteria for an interesting complex system, will be in this intermediate range between these two extremes, where there's some degree of correlation, maybe some information is thrown away, and we want to pick that out. Okay, so the strategy here in trying to get this bundle of information, the information source, across this noisy channel is, the first step, if you were an engineer, is you use, you design your code book so that you can compress out all the redundancies, remove all the redundancies in the input. Why send more bits along here if you don't have to? So you compress it down to the smallest description possible. Think of our simple 4-letter alphabet using that 4-code word code book. Then we have this smaller amount of information, raw information sitting there, think of it stored on a disk. And now we have a little bit room, since we've compressed it, we have room, we can add back in redundancy that helps anticipate the distortions in the channel, like that run like limited code. Now I occasionally have to add bits back in because the electronics needs to be synchronized. So first, strategy, compress, then kind of re-expand. You could think of it as another code book in ways that take into account the distortion properties of the channel. Okay, so let's do a couple examples here, and then I'll give you a quick overview of the and statement of Shannon's second theorem. So first example, the trivial case, noisy binary channel. So I have a mapping from 0s and 1s to A and Bs, and here's my schematic diagram here. 0, I have a 0. Input to the channel A comes out, a 1 into the channel, and a B comes out. It's this conditional distribution that describes the channel is just the identity matrix. And we can calculate the capacity here, right? Just maxing over what we could put on the input, the mutual information. Well, I choose this form to expand it. There is no uncertainty in the input given the output. If I got an A, it was a 0. If I got a B, I know it was a 1. So that term is 0. And this just boils down to the shared information just boils down to the entropy of the input. And then that is maximized for a fair coin. So I have 1 bit. So this channel, I mean, no surprise, it better work this way. This channel can transmit 1 bit per unit time, if you will. Okay, and then the source that achieves that rate is the fair coin. Next slightly non-trivial example, which is actually key to the second theorem, is a noisy channel with non-overlapping output. So here, binary symbols coming in, a 4-letter output. I just can't illustrate the idea. And so the idea is if a 0 comes in, there are certainly errors in the channel. That could be some kind of distortion. But I always get either A or B, and I get them with equal probability. Or if I get a 1 on the input, the channel, in this case 1/3, 2/3, gives me a C or a D in the output. But it's pretty clear, as the receiver, I still know what the input was. But noise has been added. You know? You could sort of think of this as like some voltage level coming in. Logic level 5 volts, logic level 0 volts, and there's a little bit of millivolt noise on there. That's fine. I can still detect 0 volt. Okay, so we can have channels that take an input message and kind of fuzz it out a little bit, but as long as the output sets don't overlap, we're fine. Right? So let's convince ourselves of that. So here's this conditional distribution that characterizes the channel, just a matrix version of that picture. Calculate the channel capacity. I'm going to use the same form as before, uncertainty in the source minus the uncertainty in the source given the output. Well, I have no uncertainty in the input given the output because the output sets don't overlap. So that conditional entropy term is 0. It just boils down to the source amount of information coming in, and that's, again, just a fair coin, and 1 bit is the channel capacity. So it's kind of a simple example, but it does hint actually at the main idea that Shannon had for this error-free. We want to choose, even if there is distortion in the channel, we want to choose code words that force the outputs into this non-overlapping subsets. Okay, now this is like a serious example here, and it's surprising that this all works even in this case. Okay, so here this is kind of a binary symmetric channel. There's a certain error probability E. So if a 0 comes in, the channel flips a coin with probability E, it makes a mistake. 1 comes in, probability E, it makes a mistake. Okay. So the capacity, we need to calculate this mutual information. Well, in this case, I can use this expression for the mutual information, uncertainty of the output minus the uncertainty output given the input. Well, so the uncertainty output, that just sits there, but this conditional uncertainty is simply given by this little biased coin flipping process, and that's just this explicit function, h of e, the binary entropy function with error probability e. So you know exactly what that is. It's symmetric channel, so you could argue that the maximum entropy on the output would be when this looks like a fair coin, so that'll be 1 bit. So this is our channel capacity here. 1 minus the binary entropy function of the error probability e. And well, you can check. It was complete distortion if we had the error here being 50-50. There would be no way to reconstruct what's going on here, because h of half would be 1. We have 0 capacity. So it's a little surprising in this case, with E being non-zero, there being any bit of error, that you can actually transmit information reliably over that. And that's sort of Shannon's main result, which we'll get to. Properties of the channel capacity. Non-negative, bounded above by the log of the size of the input alphabet or the output alphabet. It's a well-behaved function. It's continuous in terms of the input probability parameters, and also if you change the parameters in the channel itself. A very important property is that it's concave function of these inputs. Right, if this was a biased coin, I'd have probability error. and it would be continuous as I move that around. So, as a consequence of these last two properties, there is a global maximum. Right? The quantity is defined as maximizing something, and it turns out we have this nice continuous function that's concave. That means that we can crawl around as we try to do this maximization. It's well behaved. And in general, you have to use numerical algorithms to calculate the capacity for a design channel, not these simple cases we just did. So, just no closed form solution in general. But they're good optimization algorithms for it. Much more problematic if the channel has memory, however. So that's why it's often not treated, or why people try to design memoryless channels. Okay, so finally, the channel coding theorem, channel second theorem. Capacity is the maximum reliable transmission rate for a channel. And more suggestively, but again, it's non-constructive, as you can see in Cover and Thomas, there exist error-free codes as long as the code rate, the source entropy, is less than the channel capacity. So this is kind of amazing that you'd think a noisy channel would throw some information away that was irretrievable, but it turns out that there are ways of coding. And the main strategy behind this is to think of this, to set up the proof actually in terms of a noisy channel with non-overlapping outputs by using longer and longer words. So I'll give you a kind of a cartoon picture of how it works. You can take, and this is part of the non-constructive part of it. You code using very long block lengths, right? Where I'm looking at concatenated messages of length L, and then those, of course, will grow at this rate, right? So to the length of these blocks times the entropy. And then you try to choose code words for these long message words that produce non-overlapping outputs. So the basic picture is this. If this is the input space, okay, space of all possible messages of length L, okay, the size of that is 2 to the L times the entry rate of the source. Imagine this was a fair coin, right? This would be 1 bit, so I'd have 2 to the L binary messages of length L. So that's, think of this oval as all the possible. And then same thing for the output. We have this set of output messages here that we can generate, output, I should say, code blocks. And that, the size of that is 2 to the L uncertainty in the output, the entropy of the output, okay? And then the idea here is to look at sufficiently long message words such that when they get mapped forward through the distortion of the channel, they might cover a number of output sequences from the channel, but I want this sort of target to be non-overlapping with others. Now, and the trick in this, and the reason we're going to longer and longer lengths, is that these volumes grow exponentially. And if I look at a sufficiently long length, I'm going to have plenty of room to put in kind of design non-overlapping ovals, the noise fuzzed out message words. So that's the main trick. In fact, you often hear this kind of, it's a sphere packing problem in high dimensions, in arbitrarily high dimensions. Right? So put these things in different places. So that's the main setup. And just a little bit of sort of, well, I should mention here, right? So how big are these error sets? Right? If I start with this particular length L message block coming in, well, we can measure that as 2 to the conditional entropy of the output that we got, given that particular input. So we have a way of quantitatively measuring how big these things are. We know how big the whole set is. So basically, the ratio of these conditional entropies to this whole thing is going to tell us the number of how much room we have to put these non-overlapping blocks in. And that's where that's why the mutual information comes out, right? I have this space of this size 2 to the h output entropy divided by the size of these little error blobs that the channel's added for individual code words. Take the ratio, that'll be how many I can put in there, and that's just, the algebra is just 2 to the L times uncertainty of the output minus uncertainty of the output given the input, which is mutual information. So that's why the mutual information as a quantitative measure is controlling the kind of transmission rate of a channel. This kind of counting argument here is trying to pack these fuzzballs. The noisier the channel, the bigger these are going to be, so like fewer code words I could put in there, error-free. But again, the trick is that these sets grow in volume exponentially with the length. So if you're having some problem, then you just double the length. Now that's not great. Maybe that means your encoding apparatus, your channel is this horrendous thing that has to deal with bit strings of length, not 10, but 1,000. But Shannon was just trying to show that you can do this in an error-free way. And again, so then the argument is, of course, if it's non-overlapping outputs, even if it's noisy, and I see it falling into here, the whole set of code words, output words here, I know that's associated with unique input. That's reconstructible. So that's sort of my ridiculously short summary of a beautiful and important theorem in information theory, Shannon's second theorem, that you can actually do this in an error-free, reliable way. Now you might also ask, in a particular situation we're in this learning channel or talking about the measurement theory, what happens when the information source is above the channel capacity? So the example I have in mind is I have the Lagrange system behaving continuous states. Presumably these are infinitely precise states, three-dimensional space, and I put some coarse partition on that because I'm measuring with an 8-bit A to D converter. That first guess would be that the information source is, the rate of generating information would be much, much above what the instrument could handle. So presumably then this happens a lot. I mean, like the housefly example flying over the Borges novel, short story, there's this information out in the world, but its sensory apparatus and cognitive apparatus can't understand what's going on. So what happens is that, if I give a schematic answer to this general question, what happens when the information source is above capacity, basically Shannon says, oh, we have error-free. There is some way to encode the information source so that I have zero error. But as soon as you start to exceed the channel capacity, as soon as the code rate or the entropy rate of the source exceeds the capacity, then there's this irreducible error. Information really is thrown away. And it seems like this is probably typical of measurement systems. Nonetheless, we are able to learn things about the world and move through it and be effective, like the housefly is, right? So it's kind of an interesting puzzle. So there are a number of things in information theory that are very suggestive to us. Almost all of information and communication theory is working down on this error-free regime down here, but probably most of science, neuroscience, science, biosequences, DNA analysis, all that stuff, the genetic apparatus, reproduction, we're probably all way up in this range. But effectively balancing these irreducible error against information we can pull out and use to make sense of the world that get transmitted. So there's not a lot of theoretical work up here framing the problem this way, of learning in this kind of noisy environment. Okay, well, that's actually it. I can't believe we had the delays and I got through the second theorem that quickly. Hopefully it was somewhat convincing. The next lecture will be about moving more heavily back into processes. So you might want to go back to the lecture on Markov processes, hidden Markov processes. Because now we want to take these measures of information and extend them to deal with not all the IID cases we just dealt with here, memoryless channels, IID sources, but memoryful everything. And then the question is, how do we measure memory and even entropy rates correctly in that case for processes of arbitrary range correlation? So yeah.
So I'm just curious, in that range where you have lossy channels for
right.
like
Yeah, that's good. Yeah.
Is there kind of a connection to thermodynamics still in terms of
Oh.
heat and things of that sort, or is that?
Yes. So we had been using this word, and I mentioned the story with von Neumann and Shannon. This kind of rather humorous or cynical suggestion by von Neumann that Shannon should use the word entropy for his p log p quantity. Right. So this is very suggestive that there should be some thermodynamic connections. At this point, I think that would just confuse us. So first of all, there's a positive answer, yes. And it's only recently, I'd say in the last dozen years or so, that the right vocabulary has been introduced. Most of these information systems, dynamical systems, are non-equilibrium systems. So usually our notion of entropy, even the concept of temperature, is only well-defined in equilibrium systems. So we have to think about when we apply information theory analysis to a dynamical system, which is non-equilibrium, we have to be really careful about the non-equilibrium aspect of that. So I know I'm saying some things that aren't terribly clear, but there has been some recent work going back and reanalyzing Maxwell's demon, where we can start to see more clearly a relationship between, in the case of Maxwell's demon, which the demon ended up calling an intelligent being, or whatever intelligence meant in 1860, but able to sort hot and cold molecules right down the sides of the box, which then could be transformed into useful work. So that's a nice, beautiful connection or conundrum between some sort of information processing and observation, taking actions also, and being able to extract a thermodynamic work. So there definitely are connections. We'll have to kind of come up to that carefully, and we'll have a better set of ideas, clear set of ideas in spring. That all said, there are a number of projects, like working with Maxwell's demon and so on. It'll be great projects. It's really interesting. Pretty much at the research frontier right now, this trying to reunite, despite all my saying, oh, energy and information are different. In fact, it's very much an interesting and active area right now, trying to relate to two things, in particular at the nanoscale, where you have systems that are way out of equilibrium. Obviously, because every day we wake up, sort of at the molecular, being pretty effective. So what's going on? In a sense, we have very little clue about how the molecular hardware works, and it does seem on short time scales to violate the second law. But in fact, now we see them as not violating the second law, but very consistent, and just being various kinds of information-driven ratchets that can pull useful work out of the heat bath. So, really interesting topic.
Well, the way that diagram is drawn is suggestive of a bifurcation diagram. Is that accidental or intentional?
I would, yes. So, well, you said either or. It's not accidental. There is some interesting work that looks at this just close to the threshold C, just as R goes above C, as a phase transition. So not a bifurcation, but some methods in statistical physics that analyze this and can calculate the kind of error fluctuations right around that change. Yeah. So.
Did you mention that there's not like much work in the throwing away?
Well, the way I kind of characterize it, yeah.
Right. But a lot of times, like we want to throw away the right information. Like there's specific information we want to extract. Like is that something?
And you're essentially mapping yourself back down here. But yes, right. At least the way yes, right. Sure.
Like typically we don't.
Right.
You want to throw away
right.
quite a bit of your.
Yeah. We'll talk about that a little bit. There are ways, when we explicitly start talking about building models, when we have the right set of tools, we can talk about going from a process and building a model of it. There'll be trade-offs like this, like, oh, okay, I have this information source. In fact, we'll go through an example where you'll prove that it has a countable infinity of states, but you might go, I don't care about it. I can't work with a countable infinity of states. I noticed that if I use a 6-state model, I capture 93% of all the probability. That's good enough for me. 7% error, no problem. So there's a systematic way of kind of trading off model size against error rates, effective error rates, which is why we do this all the time. So, right, maybe the way I was saying it, I was kind of mischaracterized. There is some thought about trade-offs like that.
So you want to do a tracking model, careful.
Right, yeah. We choose that all the time, right.
Roll on that.
What the relevant observables are. Yeah, and that actually turns out the main technique there is due to Shannon. It's called rate distortion theory. He was interested in how to encode real numbers into discrete signals, discrete words. And that's obviously going to be fraught with error, but at least he wanted to do as good as he could. So there's discussion of that in Cover and Thomas. I'm forgetting the chapter number, but there's some. Yeah, so we'll come back to that in the spring. There's some time. Yeah, there's a way to be systematic about that. But we need to talk more directly about inference and modeling, and where we have a context in which we have that choice. So, yeah. So we will deal with this to a certain extent. That kind of trade. Okay, great. Thanks for your indulgence.